Let's review oxidation states. And if you took my Organic Chemistry 1 class previously, you might recognize this page. We did take similar notes in Organic Chemistry 1, so you can pull those out if you have it. And if not, I'm going through this sheet anyway, and we'll do some different examples that are more relevant for Organic Chemistry 2. So oxidation states, this is a property of an individual atom in a molecule. And it's similar to formal charge, but it's different. And both formal charge and oxidation states are useful in describing properties of atoms in molecules. They are just calculated a little bit differently. So formal charge, we know this by now. We do the column number of the atom minus its owned non-bonding electrons, and then subtract half of the electrons in bonds. And so the assumption for a formal charge is that the electrons that are present in bonds are shared equally between the two atoms that are in the bond. So for example, if we look at this ethanol molecule, say we want to calculate the formal charge of the carbon that's bonded to oxygen. So formal charge of that carbon. We say carbon is in column 4. There are 4 bonds. Each bond has 2 electrons. But carbon only owns half of those electrons, so that means it owns 4 electrons. Its formal charge is 0. We know anytime we see carbon with 4 bonds that it has a formal charge of 0. This is how we calculate that. For oxidation states, the main change in the assumption about ownership of electrons is that when calculating oxidation states, instead of assuming electrons in a bond are equally shared between the two atoms that are participating in that bond, the assumption is that the electrons are completely owned by the more electronegative element. So if we're looking at oxidation state of that same carbon, let's use a different color here. So oxidation state of carbon, the one that's bonded to oxygen. Now let's remember we have 2 electrons per bond. So if we kind of draw those out, we can see that the carbon, which is slightly more electronegative than hydrogen, would own, I'm going to just draw a circle to show which electrons are owned by carbon. So carbon would own both of the electrons in the bonds to hydrogen. Carbon and carbon have the same electronegativity, so those electrons are split. Each carbon owns 1. Carbon owns both of those electrons in the bond to hydrogen. And then oxygen is more electronegative than carbon, so we say oxygen owns both of those electrons in the bond between oxygen and carbon. So for the oxidation state of carbon, we start with column number, so column number 4, and then we subtract the owned electrons, which in this case is 5. So carbon has, in this bonding pattern, has an oxidation state of -1. So the formal charge and oxidation state can be different. Oftentimes they are different. Typical oxidation states for some atoms are provided here. So the hydrogen is usually +1 because it's not very electronegative. So it often doesn't own electrons in its bond. Oxygen is usually -2. And then halogens are typically -1. So let's do some examples here. You might even pause the video and try Calculating the oxidation state for the carbon that's bonded to the oxygen in each of these molecules. So we'll do an alcohol, we'll do an aldehyde, a ketone, and a carboxylic acid. Alcohols, aldehydes, ketones, and carboxylic acids are the main functional groups that we'll be focusing on for the rest of the term. So 1 propanol, we have 3 carbons. And if you're calculating the oxidation state of a carbon, I find it useful to draw out all of the bonds. So here's 1 propanol. You should be able to draw that molecule on your own. An aldehyde is where we have a carbonyl. The carbon is bonded to a hydrogen and then a carbon chain. In this case, we'll do an ethyl group. The carbon chain could also be a hydrogen, and that would still be considered an aldehyde. That is actually formaldehyde. In a ketone, I think we'll move carboxylic acid down. Ketone molecules, we have a carbonyl, and then that carbon is bonded to 2 carbon chains. Carboxylic acid, we have a carbonyl bonded to an OH group and then a carbon chain. Okay. I encourage you to pause the video and try calculating the oxidation states of the carbons bonded to oxygen for each molecule. I will go through them now. The carbon in 1 propanol owns 2 electrons in each of the bonds to hydrogen, 1 electron in the bond to carbon, and then 0 electrons in the bond to the oxygen. So it has the same oxidation state as above. Same as what we calculated above. In an aldehyde, the carbon owns both of the electrons in the bond to hydrogen, half of the electrons in the bond to carbon, and none of the electrons in the bond to oxygen. So its oxidation state is +1, so it's owning 3 electrons in an aldehyde. In a ketone, carbon owns half of the electrons in the bonds to the other carbons, and then none of the electrons in the bonds to oxygen, so it's owning 2 electrons here. So it has a +2 oxidation state in the ketone functional group. For a carboxylic acid, carbon owns half of the electrons in the bond to carbon, and then no other electrons. No electrons in either of the bonds to oxygen. So you notice that we're increasing in oxidation state when we go from an alcohol to an aldehyde to a ketone to a carboxylic acid. In the next video in this unit, we'll talk about reactions that are oxidation reactions. And in these reactions, we start with an alcohol for the most part, and we end with an aldehyde, ketone, or carboxylic acid. So they're called oxidation reactions because we're increasing the oxidation state of that carbon where the reaction is occurring.